Welcome back to AI Paper Podcasts. We're the place you come to get into the weeds on the latest AI research and really understand what matters.
That's right. And today, we're tackling, well, a pretty fundamental question, actually.
Yeah, it's about these incredibly powerful foundation models we're all working with. Do they genuinely get the world they seem so good at describing? Or is it more like very sophisticated mimicry?
It's a huge tension, isn't it?
Yeah.
I mean, these models are amazing at prediction. Next word, next game move, even predicting where planets will be.
Exactly. Which leads straight into the paper we're diving into. What has a foundation model found? Using inductive bias to probe for world models. It asks point blank. Does all that predictive skill mean they've actually found the deep rules, the underlying truths? Or are they just really, really good pattern matchers?
Okay, so for you listening, especially if you're deep in the tech side of things, here's the quick version, the sort of 1-minute takeaway for this deep dive.
Go for it.
This paper introduces a really clever new method. They call it the inductive bias probe to get at this question. And the results are, well, honestly, quite surprising.
Yeah, they found that even when these models absolutely ace their main training job, like predicting orbits or game moves perfectly, they often just don't develop the right kind of underlying assumptions, the inductive biases that match the true world model.
Exactly. It seems like they learn shortcuts. Task-specific heuristics is the term they use. These tricks work really well for that specific task they were trained on, but they don't generalize.
So, like, a model predicts planet movements flawlessly.
Right.
But it hasn't actually grasped Newtonian mechanics in a way that lets it, say, apply that understanding to a slightly different physics problem.
Precisely. Or an AI playing Othello predicts every legal move, like, perfectly. But it doesn't really understand the Othello board state in a deep way.
And that's not just academic navel-gazing, right? This has real implications for how we build and trust these AI systems, how we test them, how we think about their safety if they don't truly understand in the way we might assume.
Absolutely. It forces us to think beyond just prediction accuracy. Okay, so let's maybe set the scene a bit more.
Yeah, the paper uses a great historical analogy. Think about Johannes Kepler. Amazing astronomer, right? He spent years charting the planets, finding these precise geometric patterns.
He could predict where the planets would be with incredible accuracy.
But he couldn't tell you why. He had the what, the pattern, but not the underlying why.
And that was Newton's big leap, wasn't it? Isaac Newton comes along and develops universal laws, his laws of mechanics. They didn't just predict, they explained Kepler's patterns. And crucially, they generalized. They worked everywhere.
We saw something similar with Mendel in genetics too, right? Observing trait patterns long before the theory of genes explained it all.
Exactly. So fast forward to AI. The big hope, or maybe the assumption, with foundation models is that by learning to predict these incredibly complex sequences, they'll somehow stumble upon or learn these deeper truths, these sort of world models.
But the challenge, the absolute core of this paper is, how do we know if they've actually made that leap? How do we test if they've gone from just sequence prediction to, genuine understanding of the mechanisms underneath?
Right. It's not easy to just peek inside and see Newton's laws written down in the weights.
Okay, so let's dig into their solution. This new tool they developed, the inductive bias probe. How does that work?
Well, first, you have to think about inductive bias itself. Any learning algorithm, when it only has a limited amount of data, has to make assumptions to generalize, to extrapolate to unseen data. That's its inductive bias.
That's the no free lunch theorem idea, right? No algorithm is universally best without some built-in assumptions.
Precisely. So a world model, in this context, is like a set of rules, a structure that defines how the world works, the state space, and how inputs relate to states. Think Newton's laws for physics, or the rules of chess for a game.
Okay.
The key insight of this probe is that you can reveal a model's implicit world model by seeing how it extrapolates from just a tiny bit of new information. It's inspired by how scientists work, right?
Yeah.
We use our understanding of the world, our world models, to make big inferences from small experiments.
Gotcha. So the probe procedure itself, they show it in figure 2. It takes the foundation model you want to test.
Yep, the pre-trained one.
And it takes a postulated world model, basically, your hypothesis about the underlying rules the AI should have learned, like Newtonian Mechanics, for example.
Right, your candidate theory.
Then you feed the model small synthetic datasets. Tiny ones, but designed to be perfectly consistent with that postulated world model.
And you do this repeatedly.
Right, and then you see what function the model learns from that tiny data set, and you compare that learned function to the functions that are actually allowed by the true world model you postulated.
Exactly. And the crucial bit here, like you said earlier, it's not about prediction accuracy on one big data set. It's about, does the way it generalizes from sparse data match the patterns allowed by the real underlying rules? Does its extrapolation look like it understands the world model?
To make this more concrete, especially for, say, situations with a limited number of states, they introduced these two metrics, RIB and DIB. Can you break those down?
Sure. So RIB is respecting state. It basically asks, if two different inputs should map to the same underlying state according to the true world model, does the foundation model make similar predictions for both?
So consistency for things that are fundamentally the same.
You got it. High RIB means yes, it treats equivalent states similarly. Then there's DIB, distinguishing state. This asks the opposite. If two inputs should map to different underlying states, does the model make different predictions for them?
So can it tell things apart when they actually are different according to the rules?
Exactly. High DIB means it effectively separates distinct states. They use this analogy to precision and recall. You kind of need both. High RIB and high DIB together suggest the model's inductive bias aligns well with the postulated world model.
And this is different from older ways of probing models.
Yeah, quite different. Standard probes often just look at the model's internal activations as fixed representations. But this inductive bias probe looks at how the model behaves when it's adapted, when it learns from new, small data sets. It cares about the functional similarity, not just the internal wiring, which is, I think, a much more robust way to assess understanding.
Okay, this probe sounds powerful. So the first big test case, the one that really grabs you, is orbital mechanics. Did a transformer trained on planet movements actually learn Newtonian mechanics? Did it find gravity?
This is where it gets fascinating. They set up the experiment really carefully. They simulated solar systems using Newton's laws, recorded sequences of XY coordinates for planets over time. Each sequence was a different solar system.
And the model?
A pretty standard transformer, 109 million parameters, trained to predict the next position based on the history. And its performance, just wow.
How good?
Like R squared value over 0.9999. Basically perfect prediction of where the planets would go next. It crushed the baseline models.
Okay, near a perfect prediction. That sounds like it must understand the physics, right? But that's exactly what the probe is designed to test.
Exactly. So they ran the inductive bias probe, postulating Newtonian mechanics as the true world model. And the results?
Let me guess. Not so good.
Yeah. Starkly low inductive bias towards Newtonian mechanics. Despite predicting the trajectories perfectly, its underlying generalization behavior didn't match Newton's laws.
How did they show that specific?
Well, first, they fine-tuned the model on a related task, predicting the actual force vectors acting on the planet, a core part of Newtonian mechanics. Its performance was poor, really poor actually, as shown in their figure 1.
So it could predict where things went, but not why in terms of forces.
Precisely. And then even more tellingly, they used symbolic regression. They basically tried to ask the model, okay, based on your predictions, what is the law of gravity?
And it derived F equals GM1 M2 R2.
Not even close. It came up with these bizarre, nonsensical force laws, completely wrong. And critically, the laws it came up with were different depending on which subset of simulated galaxies it was probed with.
Whoa! So for one set of planets, it might think gravity works one way, and for another set, it thinks it works completely differently.
That's what the results imply. It suggests the model wasn't learning a universal law at all, but rather really complex, specific heuristics tailored to the particular patterns in each data slice it saw during probing. They even had an oracle model as a control, which did recover Newton's law correctly, showing the method works when the understanding is actually there.
Okay, that's sobering. A model can look perfect on the surface, predicting orbits with incredible fidelity, but underneath, it hasn't grasped the fundamental physics at all. It's just found very, very elaborate shortcuts.
It really makes you rethink what learning means for these models.
And this wasn't just a physics quirk, right? They applied this probe elsewhere, too.
No, definitely not. They looked at simpler lattice problems first. Imagine an agent moving on a line finite number of spots. They found models could show high inductive bias for a very small number of states, but it dropped off fast as the complexity, the number of states, increased.
Any difference between model types there?
Interestingly, yes. The transformer consistently did worse on the inductive bias metrics compared to RNNs, LSTMs, and even Mamba models in that setting. That's in their figure 5 and table 2.
Okay. And then the big one, Othello. Complex game, Lots of strategy.
Right. And again, standard performance metrics look fantastic.
Yeah.
Models trained on next token prediction, just predicting the sequence of moves in game transcripts, got incredibly good at generating legal moves, like nearly 100% accuracy.
You'd think a model that only makes legal moves must understand the rules of Othello, right? It must know what the board state means.
That's the intuition. But the probe told a different story. When they probed for inductive bias towards the actual Othello board state, the configuration of pieces, the bias was poor. Again, Table 2 shows this quite clearly.
But does that poor bias actually matter in practice?
Well, yes, and this is a key finding. They show that models which happen to score better on these inductive bias metrics also performed better when they were later fine-tuned on new tasks that depended on understanding the board state. Tasks like predicting who has more tiles, majority tiles, or the overall game balance.
Ah, okay. So a stronger alignment with the true world model, even if imperfect, translates to better generalization on related tasks that rely on that underlying structure.
Exactly. It shows the inductive bias isn't just an abstract measure. It has practical consequences for how flexible and adaptable the model is.
This raises such an interesting question then. If these models, especially in Othello, aren't developing an inductive bias towards the true board state, what are they biasing towards? What structure are they learning?
Yeah, the researchers had a really smart hypothesis for this, which they called the next token partition hypothesis.
Okay.
Think about Othello. It's possible for two completely different arrangements of pieces on the board to result in the exact same set of available legal moves for the next turn.
Ah, I see. Different causes, same immediate effects in terms of what moves are possible.
Precisely. The hypothesis is that the models aren't learning to represent the full board state, but instead they're learning to group states based on the set of legal next moves. They develop an inductive bias towards this next token partition, rather than the true state partition.
And is there evidence for that?
Quite a bit, actually. They showed, for instance, that when they fine-tuned the model to predict the entire Othello board, its predictions were often visually wrong. The board didn't look right. But the set of legal moves you could make from the model's incorrect predicted board often perfectly matched the legal moves available on the actual true board.
Wow. So it gets the implications right, the legal moves, even if it gets the state wrong.
That's the idea. And their refined DIB metrics back this up too. They found that inputs corresponding to different board states, but which shared the same set of legal next moves, tended to produce more similar predictions from the model compared to inputs from different states that also had different legal next moves. It strongly suggests the model is lumping states together based on the allowed next actions.
It's like it learned a coarser, more pragmatic representation focused purely on what it was trained to do, predict the next move, rather than the full underlying reality of the game state.
Exactly. It aligns with other findings suggesting models learn these sort of bags of heuristics or shortcuts, rather than deep, coherent models of the world.
Okay, so let's try and wrap up the key messages from this deep dive. Foundation models, undeniably powerful sequence predictors, they can generate stunningly accurate predictions.
But, and it's a big but, this paper really highlights a crucial gap. That prediction skill doesn't automatically mean they've learned a robust, generalizable world model that captures the underlying rules, the why.
Instead, they often seem to rely on these task-specific shortcuts, these heuristics.
Or these coarsened state representations, like grouping Othello boards by legal moves instead of the actual piece layout. They master the prediction without necessarily mastering the why, the underlying mechanics.
So for you, our listener, particularly those of you building, testing, or relying on these models, this distinction is, well, it's pretty fundamental, isn't it?
It really is. It forces us to ask, how does this gap between prediction skill and world model understanding affect how we develop AI? How do we build systems that are not just accurate predictors, but are also robust, transparent, maybe even genuinely intelligent in a deeper sense?
And maybe the next big step, the question this leaves us with is, can we develop methods that don't just test for a postulated world model like this probe does, but can actually automatically discover what implicit world model or what set of heuristics a complex model like this has actually learned from the data? Figuring that out seems critical for the future.
Absolutely. Lots to think about there.